Let me ask you a question. Okay? Anyone in chat that's using C++, why do you not want to worry about memory allocation when you're using a language like C++? Isn't that the whole point of the language? There is a person on the internet that says that shared pointer is an anti-pattern.
I have no idea, but I can tell you that I'm using normal pointers.
Get entity by ID. I love pointers because a pointer can be null. And when I call get entity by ID, I can always check if I got something back. And I implement this function in a way where if I get something back, I know that I found my entity. Otherwise, I will always return 0 and then I'm able to check this. I can do get entity by ID and check if I got it back. Otherwise, if I don't do this, I would need to create this 0 entity or a 0 return value, maybe an invalid index, an invalid entity, something. And I would have to do this for every single structure that is not a basic return value like an int, a float, char pointer, a character, something like that. And I don't like that, which is why I love pointers. And so a shared pointer, comparatively to a normal pointer, is a pattern that allows you to keep references to the same pointer from multiple locations. Let's say in a game you have a bunch of enemies and then you have a shared pointer to an enemy target from your player or from multiple players to the same target. And if the enemy dies or if you move the enemy, then you make sure that the shared pointer is still valid or not. It basically encapsulates the lifetime of allocating and deallocating and initializing and deinitializing data. However, let's not make this too long, but what I like the most, especially for shared pointers and other things, I just like big arrays. Static arrays that you can iterate over. And then they are filled at all times. And I don't have to worry about shared pointers at all. If I want to find a specific entity, I find them by a unique ID. That is a combination of a number together with an array index. And then I make sure that I never change the array index. And by the way, Pond and Pikachu, thank you guys for subscribing. I appreciate that a lot. Okay, let's see here. So I don't know what he means by anti-pattern. In my opinion, use what you want to use. Doesn't matter. If you like shared pointers, weak pointers, unique pointers, normal pointers, raw pointers, references, just use what you want to use. I always take a look at games. Undertale is terribly written, but it's still massively successful. Just use it. But okay, let's see. A brief history. A shared pointer was introduced, wait, already in 1999? As a part of the Boost library collection. It existed even before Boost had version numbers. Wow. Okay, the only alternative the C standard library could provide was an auto pointer. Okay, auto pointer became famous mainly for its disadvantages. Interesting. So standard library and disadvantages. I hear this a lot. Okay. And as a result, it was rarely used. Finally, the auto pointer was deprecated in C++11 and completely removed in 17. So in 11, you could still use it? Damn. I wonder what the default version is when you're compiling with MSVC. Boost your way into being a dogshit programmer. Okay, let's see here. In 2011, C++11, Boost shared pointer finally made it to the standard library together with other smart pointers. Over a decade, Boost shared pointer was the most used smart pointer in C++ because of the reference counting. You can be sure that if you have shared pointer active, then you're indexing into correct memory. Okay, a few words about the shared pointer, how the shared pointer works. Yeah, it's reference counting, but let him explain it. From a very simplified point of view, a shared pointer has two pointers. One to an object at the heap and another one to a reference counter of shared instances. Yeah, so let's say you have two enemies taking a look at one player. They both have a shared pointer to the player and then the reference count would be 2. Every time a shared pointer's assignment operator is called, the right-hand pointer increments its counter and the left-hand pointer decrements. left-hand pointer, right-hand pointer? Are we talking about hands or something? The right-hand pointer increments and the left-hand pointer decrements? What is the left-hand pointer? Every shared pointer has a copy constructor called the shared pointer increments the counter. Every time the shared pointer assignment is called, the right-hand... Huh? Using a smart pointer is an acknowledgement that you aren't smart enough. Okay, bro. What is the left-hand pointer? Is that my left hand? Sorry, I don't get it. Assignment operator, my bro. Left-hand assignment. Okay, I have to skip over this. Maybe there's some deep C++ stuff that I'm not aware of. Sorry, I'm using C like C++, okay? I'm not the GigaChat C++ user. It's like, how can Cakez not use the C++? I've been using C++ for 4 years, and he doesn't know what a shared pointer is. What is the left-hand pointer? Are you stupid? No. I totally do not understand that. Left pointer equals right pointer. This whole article is deep C++. Okay, well, we'll get through it though. That's why you see like C++. Okay? Every time shared pointer constructor is called, it decrements its counter. If the counter is 0, the object is deleted. Yeah, so then it calls delete. Very easy. The ideal usage. With a shared pointer, a programmer can create a variable at the heap and pass it whenever they want without caring about memory deallocation, because at some point it happens automatically. So this is something I never understood. Let me ask you a question. Okay? Anyone in chat that's using C++, why do you not want to worry about memory allocation when you're using a language like C++? Isn't that the whole point of the language? I don't understand. It makes it makes no sense to me that you would want to have a construct in C++ that is hiding memory management from you when that's the advertising point of C++. I don't understand. Isn't that why you want to learn it? So that you can learn how to manage memory properly? Otherwise, why don't you just use C#? Am I stupid? Laziness meeting deadlines? Yeah, but then use C#. I have seen Mr. Abev. Okay, I'll show you something. I have seen Mr. Abev program amazing stuff with C#. This is all in C#. This is my bot. Look, I can play this. I timed out Rico and I timed out Iffy. Works very well. I love this. It's insane. But just use C# then. I don't understand. Man, Cakez, are you hiding the memory allocation behind your allocator so you don't have to care? Why do you ask? No. So I have a bump allocator. And I allocate from that bump allocator permanently. And I have a transient bump allocator, a transient storage. And I allocate that from that every frame. That gets reset every frame. These are called persistent. Let's see here. Persistent and transient storages. But I still only have 2 allocations and I still have to manage memory in a way. When I use an array and I return a pointer to an array, I still have to manage that pointer. I still have to make sure that that pointer is valid. So no, I don't agree. I'm managing memory. I'm just trying to make it as easy as possible. So yeah, anyways, if someone understands this, it would be nice if you could tell me, okay? Isn't it fantastic? It is fantastic, isn't it? Let us see. Yeah, I don't understand, but yeah, maybe it is actually good. Let's see. Reference, counter, and multi-threading. Ooh, okay. Shared pointers are often used in multi-threaded programs, where several pointers may update the same reference counter from different threads. The counter is implemented as an atomic, if the hardware allows it, or with a mutex to prevent data erasures. Yeah, it means that only one thread at a time can increment this counter. The update of the atomic variables is more expensive than regular primitive. Aha! I see. Okay, so that's I've heard this before. Can that single allocation be done with Vulkan? Allocating only once on the GPU and then using custom allocators? Yes. Yes. So you're asking a great question. Take a look at this article here. We can read it in the future too if you guys want to. It's about Vulkan and allocating memory. In there, in the article, he talks about, I'm pretty sure, if I remember this incorrectly, then I'm sorry. He goes into pipelines and Vulkan and very deep graphics programming stuff, but he also goes into how you can allocate one page of memory. A large one, there's usually a set boundary for how much you can allocate. That's the type of memory that you want to use. There is CPU, GPU transition memory, there's GPU only memory. It's different types of memory, and then you can use that memory and sub-allocate from that allocation. Yes, that's true. You can do this in Vulkan, and that's the reason why you want to use Vulkan. That's exactly the reason. Because you can manage memory, which you can't in OpenGL or DirectX 11. Of course. And so that's my original question. Why use C++ if you don't want to deal with the memory, right? So let's see here though. Allows with the mutex to prevent data erasures. The update of atomic is more expensive. Yes. In order to see the influence of atomic counter updates on performance, I have prepared a code snippet that passes a shared pointer by value and by reference 1 million times. Okay, Cakez, there's an implicit assumption that you made a shared pointer, and other strategy of memory management are mutually exclusive. I use a bump allocator, arena allocator, simple reference counter, shared pointer in the same project. It depends on the situation. The shared pointer doesn't always use reference counting that is atomic. In GCC, for example, if the program does not use threads, it doesn't use an atomic reference counter. Well, that's smart. That's actually smart, yeah, I would do that too. Or like, if I'm a smart compiler programmer, which I'm not. But yeah, thanks a lot for the link. Sure, bro, sure. Okay, let's see here. Shared pointer retriever by value. Shared pointer retriever by reference. Void pointer. Test copy value. And then what we do? We make an auto pointer. std make shared. Int pointer with a value of 100, and we do this n times, and then we do test copy by reference. And then we have an int program that we have the n passed in. If we can find it, we do 100, and then it gives us the system high resolution clock T1 and T2. We get the time between the two time span, and then we put out the seconds. Okay, sounds easy enough. Oh wow. Atomic copy is twice as slow as the atomic reference. Microseconds. Interesting. Wow. Well, almost 1.6. If our Lord and Savior Mike Acton doesn't need any kind of skill issue pointer, then neither do we. Skill issue pointer, okay. If shared pointers are often passed to functions, it is preferred to give them by references unless a function executes in a separate thread. Now, I have to call him out here. He's doing it 1,000,000 times, is it not? 1,000,000 times. So you're telling me that if a normal person writes a program, they're gonna pass in a shared pointer 1,000,000 times? You're gonna pass it in like 10 times, maybe. Okay, 50. 100. You can get 100, but not more. You don't use more. Absolutely not. So 1,000,000? Come on. But I guess his point is that even on 100, it's still almost twice as slow. It's just to demonstrate the overhead, yeah. If the shared pointers are often passed to functions, it is preferred, yeah. Memory allocation. This is the initialization of a shared pointer. What happens in the code? The new allocates, the operator new allocates memory at the heap for the integer 42. And the shared pointers constructor saves the pointer to its memory in the stored pointer. The shared pointers constructor allocates memory at the heap for the control block with the reference counter and saves it as another internal pointer. Can someone explain... Oh, I see. Now I understand why you need 2 pointers. If we have our pointer here and it holds the counter, a type pointer t with the pointer. I always thought that counter was a value, but I guess it's not. Because if it was a value and you copy the pointer, you create a copy, then counter is no longer correct. Now you have a value copy here somewhere. This counter might actually be 5, but this counter might be 4. Which means the counter here needs to be a pointer 2 to the same memory location. So it points to something on the heap where it says, well, okay, this one is 5, and they both point towards this. Now it makes all of this makes more sense. They both point here. So yeah, that's why you also have to use it in atomic, because you're accessing the same memory location. Okay. Why is this bad? The code does 2 memory allocations at the heap for a single object. Yes. The shared pointer's data is located in the separate parts of the heap. Oh yeah, right. That's true. We have another memory block for the pointer. And that's where the pointer is. It's here. The pointer points to this. Interesting. Okay. Yeah, so now we have 2 memory blocks, and they are completely 2 different locations, which makes addressing a shared pointer much slower because you have to now load in 2 memory locations into your cache. Interesting. Modern C++ people don't care about the cache cakes. Get it right. Sorry. Okay, how to fix a shared pointer. Let me see here. The code does 2 memory allocations. The shared pointer's data allocates which potentially may lead to a higher cache miss rate. How to fix it? Make shared comes to help. Make shared. I've seen this before. I've not used this once. It's almost like the same, but make shared makes only one allocation of a continuous piece of memory used for storing both the object and the control block with the reference counter. It calls the in-place constructor for the stored object, initializing the data. The picture below shows the difference in the memory layout for... Oh, I didn't even have to write it. Okay, well, stored pointer, pointer to control block. I gotta be honest, you know, my thing is better. We have a pointer here, we have a pointer here to memory. My thing is better, okay, my picture. It's not as high quality, but my paint stuff is good. 2 different locations. Shared pointer. And then they put it together in the other one. I prepared the following code that creates a shared pointer in a loop using constructor and then using make shared. Okay, so let's skip over this a little bit. We make a vector of shared pointers of int values, then reserve as much data, and then we push back. Test shared pointer, test make shared, and then we make a shared pointer vector, and then over here we call make shared. So this one is shared pointer with a new, and then this is make shared with I. Interesting. Okay. What is the difference here? It lets it run 1,000,000 times? 100,000 times. Yours is in dark mode, that already makes it better. True. Dark mode is superior to everything else. Okay, so on the... I get it now. Okay, so testing the shared pointer, we have 200 allocations and 200 frees. 200,000, sorry. And here we only have 100,000. Yeah, makes sense. Because, well, we allocate one object together. That makes sense. The output shows 203 and 103,000. I would recommend giving the preference to make shared over creating via the constructor. Except for the cases that will be covered later in this article or in this post. For more information, make shared. Refer to... Okay. Interesting. Reference cycle. The following piece of code is a simplified example of a reference cycle. There's an instance of a struct that owns an instance of a struct B when the instance of B owns the instance of A. See, this is why I don't use shared pointers. That's why I don't use shared pointers. Is that like a pointers pointing to each other situation? Do we have a situation where we have something like this going on here? What's going on? What's this? Huh? The following piece of code, let's read this again, is a simplified example of a reference cycle. There's an instance of a struct A that owns an instance of a struct B when the instance of B owns an instance of A. So they just can go back and forth, like a child-parent situation. Also, pointer A, make shared pointer A of structure A. What is struct A? A makes a shared pointer of B, or has a shared pointer of B, and the default constructor. Ideally, after the flow exits the function test, the deconstructors of A and B would print their messages. However, the following output shows the opposite. The destructors are never called. Okay, so we make 2 shared pointers and we assign both of these pointers with each other. This is getting dumber. Really, mister? What's up? Why? This is just C++ nonsense. It's a cyclic reference. I don't know why one would do this. These seem to be examples. I can only say it in German. Das ist an den Haaren herbeigezogen. Okay. In English halt. Maybe you have to use a translator to understand that. It's a dumb example. Yeah. Ideally after the flow exists. So it doesn't call any destructor. Okay, as mentioned above, the example is simple and a seasoned developer can break the cycle by introducing a third class. More? However, reference cycles can contain a long chain of objects, making identifying them harder. When adding another type is not an option, the standard class has a weak pointer. A weak pointer does not own the object at the heap and only points to a shared pointer. The shared pointer's counter equals 1. To use the object via a weak pointer, the user has to call the lock method that creates an additional instance of the shared pointer. Thus, the caller becomes a co-owner of the object at the heap. Bro, just... I have an input pointer, bro. I just don't understand, man. Like, why would I put like another, like, I don't know, game state pointer, game state? And then in the game state, like, why would I do that? And then go to game state, I'm like, okay, input pointer, input? Doesn't make any sense to me, bro. What are these examples? And I'm not even like, okay, listen. I can always enjoy a good coffee and making fun of the standard library, okay? I get so much shit for this. It's okay. I like it. I'm having a blast doing that. But this example doesn't make any sense. What is he saying? In a code snippet below, B's shared pointer to A is replaced with a weak pointer. And then it calls both destructors. The output proves that both destructors run on the exit flow. If no shared pointers are left and the object is deconstructed, the weak pointer's lock method returns a null shared pointer. If no shared pointers are left, okay. It is essentially to check if the pointer is there before using it, and the only thread-safe way to do it is the following. New shared weak.lock. If new shared method. So you know what you should do? Listen. Okay, let's go to some code here. Let's go to some code. We do this. If input do something. That difficult to do. If I have the mutex, I set input to null pointer, then another thread tries to acquire the mutex. They have the mutex, they check for input, then they know it's null pointer now. Just lock and do whatever you want. Checking for null is irrelevant. The point is that a mutex acquires input and they can set it to null pointer to signal something. The null pointer could be a signal. There could be an else here. It could happen from any thread. It's like a made-up example. So I think this should be enough, because before we even get to this code flow, we have to acquire the mutex. Two threads could true at the same time. No, because I have to acquire the mutex. That's the point. This should be enough. Inside the section for the mutex, it would look like this. With the mutex log, yeah, that's the point. I think all you need is this. That's what I have used in the past. Acquire. Acquire, bro. There you go. Okay, let's see here. More information about weak pointer referred to C++ reference. Okay, make shared together with weak pointer. By now, we know that make shared saves memory allocations and the weak pointer can break reference cycles. But what happens when they are used together? A make shared weak pointer, I guess. In the next code sample, struct B did not change, but A is slightly different now. It has an array of characters, a string. Yeah, the method make shared and return weak pointer creates the same initial reference cycle, AB, and returns a weak and raw pointer to the A. Okay. The routine test make shared with weak prints if the received weak pointer can acquire a strong pointer and how many pointers are left. Additionally, it prints the content of a string using the raw pointer. Let's see here. We have a raw string array. I like that. I understand this. More, please. This better. And we copy over just a bunch of A's. And then in the destructor, we say we are destructing the object. And then we have a shared pointer to B. And in B, we have a weak pointer to A. Okay. Make shared and return weak pointer. We call make shared on A. Then we get the address of A's pointer and the string and the string value. So we print out the address of A and the string value, and then we make B shared pointer. We assign the B pointer in A to B and the A pointer in B to A, and then we get the number of references to A from the B pointer. We should have one reference to A. But I'm pretty sure since we called make shared, there's 2 references now. And then test make shared with weak. Oh god, what is that? Auto, raw, pointer, and weak. Create make shared. Oh god, what is this? Wait, this is just initialization of the weak and raw pointers. Cakez, this is not bad, meant in a bad way, but you're gonna become a racist if you try to make the game multiplayer before being comfortable with threads. The race conditions are gonna be so painful. Okay, one with a weak pointer. Let's see. So now that we have this returned from this as the end line, then we try to get a lock to weak, to the weak pointer. Number of references to A, strong.useCount. I'm pretty sure it's gonna be 2. Stored address. And then we have 2 different addresses, maybe? Stored address, original address of A, raw pointer. Stored by original address of A, value of string. Interesting, okay. As a result of executing this test, the destructors of A and B are called, and the returned weak pointer states that there are no shared pointers left. Number of references to A is 0. Ah, it's 1. Okay, so it's not 2. Okay. Only the content of A string is still untouched. Some operating systems do not clear the released memory, but mark it as free. After I rewrote it with a custom free method that zeroed the memory, the result was the same. The memory was never freed. Ah, I see. Whenever we delete A, that's when it gives us the string. I understand now. So a weak pointer to a C array does not free the memory of the C array. So the memory location still contains... I see what it is now. I get it. Okay, let's visualize this example. I think this is actually interesting. So let's say we have A, right? A. And the first part is the pointer. And then this part here is the string. And you know, I guess A is this big. Let's make A this big here. That's all of this is A. Now, as long as we are holding, I think this is a weak pointer or a shared pointer, a weak pointer here. In the string, there could be something like his A's, right? And what he's saying is when you delete this weak pointer, this is still here. It's not freed. It contains the data still, which is what we see in the output here. But the stored address is 0. So basically what it did was it took this pointer that had a number and turned that to 0. Basically turned it into a null pointer. A C++ null pointer. Okay, here's the explanation. If any weak pointer references the control block created by a make shared pointer, after the lifetime of all shared owners ended, the memory occupied by T persists until all weak owners get destroyed as well, which may be undesirable if size of T is large. Interesting, but shouldn't the weak pointer... Shouldn't this be gone too? We are creating 2 objects here. We are leaving this function. Shouldn't both of them be destroyed? As mentioned before, make shared saves the object, the stored object and reference counter in a single piece of memory. On one hand, the weak pointers need access to the reference counter to track the availability of strong pointers. On the other, it is impossible to free a part of the memory allocated within one malloc call. The only possible solution, I see, is to call the object's destructor explicitly, but only to clean the memory once there and no weak pointers. But only to clean the memory once there are no weak pointers left. So you know what I guess from the article? This stuff is freaking difficult, man. That's spaghetti code. This is the definition of spaghetti code. You tell me I have spaghetti code? Bro, it's like, it's everywhere, bro. How? Like, goddamn. It's crazy. Like, whoa. I agree. Yeah, right? Like, am I stupid? I think it is. Okay. Thus make shared and weak pointer do not coexist. Well, design problems. Okay, the most severe problem with shared pointers is not implementation nuances, but the need for their usage. A shared pointer makes it almost impossible to track the owner of the objects. Shared pointer ownership breaks the single responsibility principle, and Sean Parent said... Who's Sean Parent? Let's see here. Sean Parent, STD... Okay, so a book writer about C++? That was bright, bro. Works at Adobe. Okay, that's enough for me. Okay. Let's see. Shared ownership breaks the single responsibility principle. And as Sean Parent said, makes the object at the heap a global variable because it is potentially accessible from everywhere. I don't hate global variables. I have a game state that's global. I think that's fine. Look, hey, let's clean up the code here. Okay, I don't want to break my game just because I put some weird code in here. All of a sudden input is null. I'm like, hey, what happened? I can't run my game. Here, have a game state pointer. Every single function can access this. I love it. It's awesome. I don't need to supply this to every function. Look, get entity by ID, access to the game state. Easy. I do it. It's everywhere. It is everywhere. And I love it. It's awesome. You can't have spaghetti code if everything is in a single file. Exactly. Exactly, my man. You're right. 100%. My point is that knowing all of these things about the memory, and when a weak pointer accesses a shared pointer, when a shared pointer is used by something, how the shared pointer behaves in situations where nothing points at it anymore, make shared, std shared, all of these different examples just add a bunch of things to learn about just allocating memory, just pointing into an index of memory. And I think learning all of these different things, that's where the spaghetti comes from, because there's so many rules. The rules apply differently depending on what you do. And with a pointer in C++, either it exists or it got overwritten and is no longer valid. Or it's null. There's not much more you can do with a pointer. I think it's much easier. But anyways, okay, design problems. It's a global variable. I think only a few justified cases of using shared pointers. Okay, let's see. Shared and weak pointers can be handy for implementing a generic cache mechanism, where the producer of the cache is not the owner of cache data. Interesting. Boost all ASIO. Boost ASIO is another excellent example because ownership of object in an asynchronous environment can be pretty complicated. This is probably the reason why most tutorials use shared pointers. Conclusion. I want to summarize the general recommendations for using shared pointers. Give preference to objects with atomic storage duration over any pointers. What does that mean? Automatic. Sorry, automatic. Then I need to read it again. Give preference to objects with automatic storage duration over any pointers. Automatic storage duration meaning what exactly? Basically, handles are better than pointers. The handle should be an ID, which is an index, and a revision. When you try to access something that doesn't match the revision, it's an invalid handle. Yeah, Jacob, exactly. That's why an ID is also an array index. You can put the array index in there. You have O of one way to find the correct unit, and then if it's not there, then you say, okay, well, it's null pointer. It's invalid. Something else there now. So I'm referencing something that doesn't exist. It's so simple. It's genius and simple. I love it. Works everywhere. He means things like std vector immo, an automatic storage duration over pointers. I don't agree with this then. So if this is referencing something like a vector, I would use an array and pre-allocate a bunch of data in an array. But okay, I mean, this is preference. You know, like this is subjective. Anyone has their own opinions. In case of a pointer is needed, go first for the unique pointer. I would go for the raw pointer, my friend. Go for the raw. Bear in mind that the overuse of shared pointers may lead to reference cycles. Greetings, my man. Thank you so much for following, Techno. Prefer make shared over the constructor to save memory allocations. Yeah, I learned that today. That's awesome. Pass shared pointer by a constant reference unless it's a separate thread. Yeah, I mean, this is just being const correct. I think it's good to stay const correct, even though the const keyword can be annoying. It can actually be annoying. But I like const correctness a lot. It also looks better in Visual Studio Code. That's just a preference, you know, if I have something that's const. It is a nice color blue. Let me show you const. Yeah, here. Look how cooldown has a deeper blue than the rest, indicating that it's const. I like that. Now, unfortunately, it doesn't work on parameters. That's an oversight by Microsoft. But when have they ever shipped a quality product lately? So, whatever, right? Check the pointer returned from the weak pointer lock before using it. Or use a raw pointer. So basically, if I were to give recommendations here, it would be use arrays, raw pointers, and IDs. IDs meaning array index plus a counter value that keeps counting for each new object. Index into the array at the index. If the ID is different, C-style programming, yeah. Return null and use normal pointers. And then you don't have to learn this. Good. Anyways, update. I've been honored with an invitation to speak at the Core C++ 2022 conference. Damn, you can check out my talk at YouTube. Oh, we could have watched a YouTube video too, but we read it now. Okay. Well, this is the article, guys. Shared pointers are evil. Well, I'm telling you now that a normal pointer, they will never lie to you. Okay, they can only be there or they're not there. That's what they do. They're honest. So use them.